So clearly, not all of our speakers got a memo about how they were supposed to dress. But our next speaker took this seriously. Our next speaker has been developing for Apple platforms for a long time. Her first WWDC was in 2006. Yeah. She left big tech earlier this year to work on as an indie developer, and her first app is a to-do app. Here to talk to you about rendering maps from data, please welcome Amy.
Thank you. Hi. Is this clicker going to click? No, it's not. That's sad. Wouldn't be a talk without some tech difficulties. If it doesn't work, I'll do it with the arrow keys. Yep, there we go. So yes, that's me. I guess you're wondering how I got here. So I came to Anvil to raise the fortunes of my noble house, House Elian of the glorious nation of Dawn. I'm the seneschal, and I have to gather enough money that my Earl can spend it whenever she wants. And yes, if you hadn't gathered, I'm talking about a LARP game. So I played this character in Empire LARP, and thought I'd come dressed appropriately. Empire LARP is one of the 3 biggest LARP events in the UK. So we gather for a weekend 4 times a year, and everyone pitches their tents and has glorious battles, does political intrigue. And there are 1,600 in-character tents in that field. And 4,000 players attended the last event, so it is big. And we have many places where you can go, many shops, many like trading houses, tea houses, and finding your way around this field is difficult. So I made a map. Every event I make the Anvil map. I map every single tent, every single business, and show people where to find things. And I print these out. These are used in the field. They're pretty huge, very, very popular. People buy them, put them up in places, use them to find their way. I print them out on a big printer like this, and I sell them for lots of these. So you might ask, how do I make this map? How do I get all the data? Well, the actual layout of the field, obviously you can find that on OpenStreetMap. You can find out where all the hedges are and the edges of the field. How do I find out where all the tents are? They release these camp plans shortly before every event, usually only a couple of days before. We get these plans telling people where to pitch their tents. And the camp plans, they are not exactly geographically accurate. They're sort of, they're more like guidelines. And then everyone turns up in a field, tries to make sense of this, and tries to put their tents where they go. And so you might ask, well, if I'm making maps out of these camp plans and some real data and that kind of thing, this is like an art project. This is not a thing a developer would need to do. Why don't I just use Illustrator to do it? One of the problems is the camp plans aren't quite geographically accurate. They're more like a sort of schematic diagram. So you can't just rotate and position the camp plan on the real world. It doesn't work like that. There's someone's diagram that makes a map that people can read to position tents. And also, my maps, I tend to restyle them every event. I make them look a bit different and that kind of thing. And if I worked using Illustrator, it would be a lot of work to go and change anything. And I need to track some additional data that's not on the camp plans. The camp plans show who is camping where, but I want to know what business they run. Are they a trading post? Are they a tea house? Are they a place that sells food? I need to keep hold of all this data and somehow integrate it. I don't want to do that manually. And to some extent, I'm a developer. I'm an iOS and Mac developer. This is how I solve problems. So I did try using Illustrator. I tried overlaying the camp plans. This was my best effort, and it's not geographically perfect by any means. And in doing this, I realized just how much work it would be. So I'm not going to do that. It's too time-consuming, too inflexible. So I wrote an app. As you do, I wrote a Mac app. And I've got this app called Forge. It's called Forge because the town that we build on this field is called Anvil, and, a bit of a pun, why not? And so Forge, it lets you position where the area that you're going to map is going to go. It lets you import the camp plans and then place these datum points that sort of map the camp plans to reality. And the more datum points you have, the more different bits of the image get stretched and squished. I've got my database powered with core data and Cocoa bindings, in order to store all the extra information I need. And then I've got this editor which lets me place tents on top of the camp plans and drag them around. And then I can also switch to showing the sort of geo-accurate version of it. I've got a thing for editing the text labels. Where do they go? And one more thing. This whole thing to actually render the map output, I wrote my own scripting language. This lets me access all the functionality of my app for loading and processing data, but also lets me access any core image filter that I want. So amongst all of this, I can make maps like this. I think that looks rather good. I mean, I know I'm speaking highly of my own work, but I'm very happy. And I can do it quickly. Once I've got the styles programmed in, which I already have, for new events, I can load up some camp plans, trace the tents on them, and then position the text labels, and then we get a map out of it. So that's what I'm doing. And this presentation is going to be about a lot of the different little things I've had to solve to be able to do this. There's maths. I'm not giving this presentation so that you will understand the maths. I'm giving the presentation so that you'll know what's possible and that you'll look up the maths on Wikipedia. So I'm now going to have to go over here because I'm going to need notes for the rest of this. Much as I would love to be able to remember everything, it doesn't always work. First of all, then, let's talk about map projections. We're going back to basics with what a map is. So the world is obviously a three-dimensional sort of sphere thing. And a map is flat and two-dimensional. So we need a way of going from latitude and longitude, which, as you're probably aware, they're how you define a coordinate of something on the world, to an x and y position on our image that we're going to make. So latitude and longitude are, as I said, coordinates. They represent a position on a sphere, which is the surface of the Earth. So latitude is how far up the sphere you are, and longitude is how far around it. And you've probably seen latitude and longitude coordinates. You can find them in all kinds of places. You can find them in Apple Maps or any map software. You can probably find the coordinates for something that you're looking at. And it's a good job that there's just one universal standard for coordinates, isn't it? Now, that's kind of accurate. There are actually quite a few, but the one that nearly everyone uses is WGS84. This is the world's geodetic system. They've made new versions of it every so often as they make more accurate estimates of the shape of the Earth. So I said two slides ago that the Earth is a sphere. I think I said a kind of sphere thing. So it's not actually a sphere. It's a bit squashed. And one reason that they've made new versions of this coordinate system is when they get a better idea of just how squashed the Earth is. But anyway, all our devices, all our map apps, and all that kind of thing use WGS84, so we're going to run with that. So there's a lot of things in working with map data that are a bit of a hassle. And for example, I just said that the Earth is not quite a sphere. That means that it doesn't have a consistent radius. So you could write a load of code to work out the precise radius at any particular location on the Earth. And you can use a bit of maths like this to do it, but I'm not going to bother. I'm going to define a constant which is close enough. Because I'm making a little map of some tents in the field, there is not going to be any conceivable world in which calculating a more exact Earth radius than this is going to change my map in any meaningful way. And you'll see this close enough image throughout the presentation. There's a lot of things where doing it actually properly would require a bit more maths than I care about. So going back to what a projection is. So I've mentioned it's taking the latitude and longitude and going to an x and y position. So latitude and longitude are positions on the surface of a sphere. So they're kind of 3D things. And we're going to this 2D x and y position on a map. And people have been trying to work out the best way to do this since, the 16th century or earlier. There are loads of ways to do a map projection. And projection just means the algorithm for turning the position on the globe to a position on a flat piece of paper. And all of the projections have trade-offs. There is no one that's better than the others for every given situation. So let's have a bit of audience participation. Does anyone know the name of this map projection? Yep, it's Mercator. Does anyone actually think that the country of Greenland is bigger than the continent of Africa? Nope. Well, if you looked at this map and were unaware of its trade-offs, you would think that, because Greenland looks freaking huge up there. So one of the drawbacks of Mercator is that the sizes of things are not accurate. Things look bigger than they are the further away from the equator you get. So you might say, well, why use it at all? And Mercator was invented for sailing ships. Mercator maintains navigational angles. So if you're sailing your ship in what looks like a straight line on the map, it looks like a straight line in real life. And that's not true of some other projections. So Mercator's great if you are sailing a boat. Sailing a boat pre-technology, you're going to use a sextant and a compass and all that kind of thing in order to navigate. This is the map projection for you. But yet, somehow, this has become the fairly de facto standard, and we still use it today. So there's loads of different projections, as I said. This one is the good homolocene projection. This one is equal area. So on this one, the size things look is much more accurately the size things are. And as you can see here, Africa looks as big as it should look, and it's kind of dwarfing the size of Europe. We can't really compare it directly to Greenland, because Greenland is actually split across two of the little bits of the map. And that is one of the downsides of this projection. Now, for most projections, the trade-offs get worse as you get nearer the poles, nearer the top and the bottom of the Earth. Also, the further zoomed out you are, the more the choice of projection will play a part. And so we're making a zoomed-in map. We're not near the poles, so any projection will be close enough. So that's what map projections are. Now, why am I talking about them? Because we're going to do maths to actually render things on a map. So just a bit of housekeeping first. Let's talk about some data structures we're going to use. CL location coordinate 2D. This is provided by the core location framework. And this is just a data structure that contains a latitude and a longitude. And those are measured in CL location degrees. Those are just doubles. So just for convenience of knowing that my data is in the right type, we'll show everything in here. I could just represent it as two doubles, but Apple's given me a nice struct, why not use it? Now, in this talk, I'm going to be talking about actually drawing our maps directly with core graphics. You might say, why not use map kits? If I was making an app that had like an interactive map, what's known as a slippy map, which is sort of an infinitely zoomable and scrollable map, yeah, map kit's great. That's not what I'm doing. I want to take some data, process it myself, and output an image. But MapKit might still have some things to help us. It might have some useful utilities. But first of all, we have to ask the question, which projection does MapKit use? And if we look in the documentation, we can see it uses Mercator. And that's Apple's diagram of what the Mercator projection is. But yeah, like Google Maps, like Bing Maps, like most of the other modern mapping software, it uses Mercator. So now we know that, but we also know that we don't really care too much about the projection, given that my map is quite zoomed in. So yeah, that's cool. We'll run with this. So now I'd like to introduce you to MKMapPoint. This is another data structure, and MKMapPoint has an X and a Y position, which is what we want, and you can init it with a CL location coordinate 2D. And it does the projection maths for you. And you can also pull the coordinates back out of it if you need to. So this is great. Apple has already coded the map projection, so I don't have to. And again, this is from the documentation. Apple say about MKMapPoint, regarding the X and Y position, what is the units, what is the scale? And Apple say, you don't need to worry about the underlying units directly. Use map points primarily to simplify computations that are complex to do using coordinate values on a curved surface. By converting to map points, you can perform the calculations on a flat surface, which is generally much simpler. So that's what Apple intended you to use it for. But I am also using this, as well as for a bit of calculations, I'm using it to work out where to draw things on my flat canvas. Now, there's one more thing that we're going to need before we can draw things on our canvas. So we can convert our coordinate points into MK map points. But as I say, we don't know the scale of the X and Y positions of the MK map points. And the scale of those, in order to translate it to an actual pixel value you can draw, is going to depend how big your map is. If I've got a map of the whole world and I try drawing a tiny little square somewhere, it'll be near invisible. But if I've got a map that's only like 20 meters wide, that same square will be much larger on the paper. So in my app, everything goes through this map object. And in order to know where and how big the map is, I store the center, the width in meters, the height in meters, and the rotation. This is for any map I'm outputting. So the center is latitude and longitude. It's a position in the world. Width and height are in meters, again, relating to the real world. The rotation, if it's 0, then north is up, and so forth. And then I also store the pixel size that I want to actually render things. So we're going to need this a lot as we go forward. So now, let's get to something a bit more concrete. So I've got this project function. And this is another slide of slightly mathsy code. This one's not too bad compared to some of the others. But this project function, as you can see, takes a coordinate as input, latitude and longitude, and also the map object so that we know how big the map we're drawing. And it returns the CG point that should tell you where to draw that coordinate. And we start by getting MKMapPoint to actually do the map projection. And as I say, it does it for us, so that's it. That's all we need to do. We are map projecting the center point of the map and also the target points, the thing we're trying to find. And then we need to work out the rectangle for our map, but in map point space, in the map points coordinate system. And again, this is fairly simple. We're working out like the distance across the map by translating our center points in meters to a new location. And then we just do a little bit of calculation to work out the scale factor between map points and my core graphics pixels. Don't worry that I'm glossing over that slightly. And then finally, we just do some linear interpolation between the two rectangles. We've got the rectangle that's the map in map space and the rectangle that is the output rectangle size in pixels that we want to draw in. Now, this code is not technically correct. I am simplifying things by rotating the target point rather than rotating the rectangle that the map exists in. But as is a running theme, it's close enough. So in that previous code, there are two bits which are functions that I haven't explained yet. I'm not going to actually show you the code for these right now, but they essentially use some trigonometry to rotate and translate things in map point space. So the translate one will translate by a certain distance at an angle of your choice. The rotation one will rotate it around a center point. And yeah, I don't think that that's going to be the most interesting thing in the talk to actually go into. So I'm going to assume that if you're wanting to do this, you can work out how to write them. So let's put it together. Let's show how this actually works to let me draw something. So suppose I'm looking to draw Glory Square. This is a big square that we have in our LARP event. I have opened Bing Maps, and I've drawn the outline of it. The reason I chose Bing Maps is because their aerial satellite photos were taken on a very dry summer, and you can actually see the paths that we all walked in the event. They obviously went and scanned it like a week after or something. So anyway, I've drawn out where Glory Square goes. I could have gone around with my phone and actually used the GPS to look for actual coordinates, but no, I've cheated and just used this satellite image. By the way, Glory Square is not actually a square, it's a rectangle. We tried to call it Glory Rectangle for a bit, but everyone found the name too silly, so we've gone back to calling it square. So Bing will let you get the latitude and longitude for any point. So I'm just going to go and right-click on each of those corner points and copy the latitude and longitude. And then I'll write a little bit of code. So I'm making myself a CG context. Have most of you familiar a little bit with core graphics? Yeah, a bit of a vibe of yes. CG context is the thing you draw into. It can represent like a view on the screen, or it can represent just an image buffer. I've got a helper function that creates one to the right size for my map, but again, that's not interesting code. You can create a CG context of a given size ready to render into an image. So, set up my line width, and then I make the coordinates for my corners. And then it's literally, in the context, I do move to the last one. Then I add line to each of them in order, and then tell Core Graphics to stroke the path to make an outline drawing of it. And if we then output that as an image, we get something like this. And that is what we were looking for. Now, you might say, how do we know that that's right? It's just a boxy type thing in the middle of a white square. So I'll draw some of the other things that go on the map, like some of the hedges and trees and some of the paths. And yeah, that's starting to look like what we wanted. This is the thing we wanted to draw. And if we compare that to our Bing screenshot, I've slightly rotated the Bing screenshot to match. And I'm falling off my little box. And you can see that we've drawn a map of that. Now, you only saw me draw the box. You didn't see me draw the hedges and trees. I'll sort of cover that a little bit later. So yeah, that's good. And you might say, why does it have to rotate it a bit? Essentially, I already had in my map app a predefined map that was slightly rotated, because this is what's most useful on the actual field. So I just reused that. Now, those of you who have thought about such things might think, well, I'm drawing these lines in 2D. I'm just drawing lines in Core Graphics between these points. Surely in the real world, those lines would be curving around the surface of the Earth, and I should use some more complicated maths. Close enough. Especially when you're this zoomed in, there is no conceivable world in which those tiny short lines would vary by even a pixel if you calculated it with the curvature of the Earth taken into account. So that is how we can draw in Core Graphics data that we've got that is using latitude and longitude to define its points. And that's the foundation of what I do here. Now, I cheated and used, I say cheated. I used the MapKit projection because it was easier. What if you did want to write your own projection? How complicated are they? So you can hop on Wikipedia and you can look up any projection. And they all have some maths like this. This one is not too difficult as projections go. This is called the bond projection. The time you might want to use the bond projection is it maintains accurate shapes of areas along the central meridian and the standard parallel, but it progressively distorts as you get further away from these regions. So yes, a bond projection formula is just on Wikipedia. This is literally copied off Wikipedia. And we can turn that into Swift code. And that Swift code is literally me translating that maths into Swift. Now, for doing this, I've actually refactored out the linear interpolation we have to do in order to get the units to be the same units as my core graphics. We still have to do that, but once I started writing lots of projections, I factored that out into its own function, because that's always the same. So yeah, this will let us run our own projection. And this is the equivalent of what mkMapPoint is doing when you initialize it with the coordinates. So what does it look like if we render our map using this instead of mkMapPoint? So we've got mkMapPoint on the left, and we've got the bond projection on the right. Actually looks pretty similar. It looks a tiny bit differently rotated, but it's not really obvious what's going on. So let's try a bigger map. This is the continent that the Empire sits on in our fantasy land of this role-playing game. So yeah, we're looking at something continent scale here. The island down the bottom is actually about the size of the Iberian Peninsula. So this is pretty huge. And you can see that things are fairly different between Mercator and Bonn. With the bond projection, compared to Mercator, the things lower down seem to have got stretched a bit bigger, and the things further up seem to have got squashed a bit smaller. And you know, it's arguable which is right and which is wrong. There's no universal, this one's correct. I recommend just going and playing with them. You can get, as I say, get all the formulae off Wikipedia. So I said that this was continent scale, so let's just show you. This is the data that I rendered that map from. This is an app called JOSM, which I'm going to be showing you a bit more about later. And the scale in the top left, you can see 400 kilometers. But you can get much more of a sense of the scale if I overlay it onto the real world. So that's the Empire continent over the top of the UK and the edge of Europe. So yeah, you can see the size that we're working with here and get an idea of how much the different map projections change that. So now I've shown you JOSM, let's talk about what it's for and how OpenStreetMap comes into play. So JOSM is an editor for OpenStreetMap data. You don't have to then submit the data to OpenStreetMap. You can just save it as a local file. So I can play about with my fantasy data all I want, and that's fine. It's a Java app. It's got a bit of a weird UI, but it's the most accessible one that I've found for sort of getting used to. So I could use JOSM. I could have drawn my glory square in JOSM. Then I would have been able to export that data, and I could have imported it into my app, rather than hard-coding those coordinates before. But you can also do things with JOSM. You can actually download the data from OpenStreetMap. So you select the area you want to download, and then you get some OpenStreetMap vector data. And if I wanted, for example, some field boundaries or the edge of the woods or something like that, I could download it like this. I could select what I want, move it to a new layer, and save it as a file. And when I say save it as a file, that's, you might be thinking that we're now going to start importing this OpenStreetMap data into our app. You'd be right. So what types does OpenStreetMap have? It has nodes. Nodes of a single point. They have a latitude and longitude. A way is an ordered array of these nodes. So it might be a closed way, in which case it comes back and finishes where it started. Or it might just be, like if it's a hedge or something, then it would just have two different ends. OpenStreetMap also has these relations, and we'll touch on those again a bit later. Those are multiple ways that form one thing. So for example, if you have like a parish boundary, or like an administrative district, something like that, that might be formed of multiple ways because it might follow a riverbank for a bit and then follow the coast, and then go onto like an artificially created line. And these things that it's following, those bits of data would all be separate ways, but the relation ties them together to form one thing. And then you can also have tags, which are key value metadata. And those are super useful, because if we're working in something like JOSM, and then we want to import that into our own app to render things, we can use these arbitrary key values to put whatever data we want so that we know that, oh, this thing should be rendered with this line color or whatever. So OpenStreetMap is XML. It was invented before JSON. And I'm not going to go through the code for how we parse the OpenStreetMap XML. It's not that difficult to parse. It's, in my app, I'm using Swift's XML parser, and it works fine. So let's talk a little bit about the kind of data we're getting in then. So as I've mentioned, OpenStreetMap nodes all have latitude and longitude. And they can all have these tags, these key value pairs for putting in our extra data. And so one thing you might want to do if you're importing some OpenStreetMap data, you might want to iterate through all the coordinates in a way, project them using that function that we looked at before, the project function, add those to a CG path, and now we're rendering polygons. And so that's essentially the same thing we did to draw Glory Square, but you can do it by importing this data in OpenStreetMap format. Now, you could, if you wanted an app that did like dynamic things with maps, so like suppose you wanted an app to run on your phone that the user can sort of set any location to do map stuff with, you can download OpenStreetMap data live and just process the same format of stuff. You'd have to find an OpenStreetMap server with usage limits that are compatible with your app. I'm doing it all essentially offline in JOSM because I only need to make these static images. So as I mentioned, relations are trickier. Just to explain to you that relations are trickier, not to tell you how to do it, but just to explain the concepts. So yeah, relations in OpenStreetMap, you make a boundary or area out of multiple ways. They can share edges with other relations or just other ways that are used for other things. For example, a parish boundary that hugs the coast. They can have holes in them, so if you're doing like a relation that was the land of an island and then there was a lake in the middle, you might knock out the lake, so it'd be like a hole in the actual thing you're rendering. The reason that they're really tricky to process is they store their ways as essentially unordered. They've just got a big bucket of ways, and you've got to work out like how they connect together. And there's some information on the OpenStreetMap wiki. This is 1/2 of the algorithm for processing relations. It's tricky, a pain in the bum, but it is doable. I suggest if you're wanting to do this, you go on the OpenStreetMap wiki and follow the algorithm as described there, like to the letter. I made the flowchart, but that's essentially the same as the text that is on their wiki describing this thing. And again, I'm not going to go through the code, but you can see by the amount of commented out print debug statements that it took me a while to get this working. If anyone is interested in doing this, feel free to drop me a message. I will happily share the code. It's just that if I spent 15 minutes talking about this, I wouldn't get through the many other things I want to talk about. So what about drawing things where we know where they are and we know the size of them? And so I'm talking about things like tents and trees. For a tent, I don't want to go and get GPS coordinates for each corner of the tent and like translate things to find that. What I want is a single GPS coordinate for the center of the tent, and then I'll know that the tent is a 5-meter tent and it's facing this way. And so what we want to do for that is work out the location that we're going to draw, but then do the size calculations and actually render the thing in 2D as using core graphics. So what do I actually store in my data model for tents? This is the tent's data for my map. And you can see that some of these things are two nodes, the blue one and the yellow square joined by a little line, and some of them are three nodes in a right angle thing. Essentially, the round tents are two nodes, the square and rectangular ones are three. And so what I'm actually storing is I'm storing the center point of the tent, that's the blue dot, and then the other node, the yellow dot on our two-dot tent, that is showing the radius of the tent and also the direction that it's facing, so the direction that the door opens. So the second most useful function in the app, so project is the most useful. We love project, that tells you where to put something. But we also want to know the sizes from something. So I've got this pixels for meters function. And so it takes a CL location distance, which is just a value in meters, and it outputs how many pixels that should be in my core graphics context. So this is super useful. I use it all the time. So let's have a look at some interesting bits. What I'm essentially doing in this pixels for meters thing is I'm making another point that's the right that's the distance I want to find away from my map in the direction that the map is rotated. So essentially, I should have put another close enough slide here, really. I'm not doing this accurately for like how many pixels it is for the meters in a certain direction. I'm just hard coding it to the direction the map goes. So I've got this location by adding distance bearing. This is quite similar to the function that I showed you before when we were looking at the projection. I said this one works in coordinate space rather than map point space. And this time I'm going to show you the code for it. So location by adding distance and bearing. We start by making sure that we have all our angles in radians. So those of you with a mathematical inclination will know that doing various calculations, especially trigonometry, on angles, you want to specify the angles in radians. For those of you who aren't of a mathematical bent, you'll know that a circle has 360 degrees to get right around. If you're measuring in radians instead of degrees, it has 2 pi radians. And this just makes the maths easier. It's fairly trivial to convert degrees to radians. I've written helper functions to do it. So we make sure we have all our angles in radians. Now, I say angles. That includes latitude and longitude. And you might be thinking, aren't they points? Are they really angles? Yes, they are really angles, because they are essentially angles on lines that come from the center of the Earth. And then, here's how we actually do the work, working out this, this distance. This formula is known as the inverse forward Haversine formula. As usual, I found it on Wikipedia and converted it to Swift. And this formula will tell us, well, it'll let us go from one point to another that's a certain distance away. And so all I'm doing in this function is I'm deriving my other point that's the distance away we care about, projecting both of those and essentially just subtracting and using a bit of Pythagoras to work out the distance in pixels. So this is how we work out how big to draw something. We know if we've got a 5-meter tent and we pipe 5 meters into our pixels for meters function, we'll get out how many pixels wide that should be. So if we're just rendering a circle, then yeah, we call pixels for meters to get the radius of it, use project to get the center, and now we're in core graphics land. We know how to draw something with a center and a radius. And for bell tents, which are the round ones, what I do for those, because they're essentially like working with a circle, I'm drawing them with like a number of different segments going around just because it looks aesthetically pleasing. So to draw those, we're going to use some polar coordinates. Again, this is another maths thing. I told you to ignore all the maths. This is just to show you that it exists. So polar coordinates, essentially, they're coordinates where you've got a center point, and you know how far out and how far round something will be. So I've got functions, again, helper functions to convert between polar and Cartesian coordinates. So to draw my bell tent, I choose my number of segments, and it's just based from what looks good. Work out the angle per segment by dividing my 2 pi radians, which is the complete rotation, by the number of segments. Iterate per segment, use this polar to Cartesian helper function to find the point that's on the edge of that segment. And then I just draw a little Bezier path using add quad curve. That's Core Graphics' Bezier path function. And then I can draw nice tents, nice bell tents, facing in whichever direction I like, that are the right size. And you can see on this map there's also some trees. Trees, in my map system, are just bell tents with randomness. We make each segment a random size and have a random inset or outset, and then just use the same Bezier point. So, yeah, random size and distance of each segment. That guesses the shape of our tree. We fill it with a texture. One of the benefits of this is that every time I render my map, the trees are actually different because the randomness changes. If you didn't want that, you'd seed the random number generator. Yes, so we're making good use of Core Graphics' Bezier curves. So, working with camp plans. As I say, these camp plans come in as diagrams that are not quite geographically accurate. Click, click. Why can I no longer click? There we go. Let's use that instead. Yeah, so we can't do a simple transform to put them where we want. We need to stretch and squish them in different ways. And I mentioned before, we've got these datum points that are points where I know the real-world location and I know the location on the camp plan. So yeah, I'm calling them datum points. They're a link between the camp plan and real life. And what we do, once we've got all of these, we need to be able to position any arbitrary point we then look at on the camp plan somewhere in real life. So we do a thing called triangulation, where we draw triangles between the points. And the specific kind of triangulation we're using is Delaunay triangulation. And this particular one is good because it avoids triangles that are long and thin wherever it can. I didn't write this one. I used a Swift package. There's a Delaunay triangulation Swift package that exists. Use that. So to go from a point on our camp plan, on our sort of inaccurate schematic, to a latitude and longitude, so each datum point knows its CG point location on the camp plan and its latitude and longitude, because I've made that mapping. That's for the datum points, but we want to do an arbitrary point between the camp plan and real life. So we run the triangulation on the latitude and longitude coordinates of all the points. That way we've got our sort of triangle mapping. And then to locate an arbitrary point, we find which triangle it's in 2D space this time. And then we use another named algorithm, barycentric coordinate interpolation. And that's essentially how you do something that's like linear interpolation, but inside a triangle. Again, ignore the maths. This is the formula for barycentric coordinate interpolation. I got it off Wikipedia, running gag. And the output of this will give you the place you want to put your thing. You can do it in either direction. Obviously, you can do it by putting in a latitude and longitude and getting out a point, which is what we're doing here, or you can do it vice versa, put in a point in the camp plan, get out a latitude and longitude. And yes, so how I use it in the app, user, which is me, because I'm the one who uses the app, puts a tent on the camp plan. We use triangulation to convert the pixel location to a latitude and longitude, using that function I just showed you. And then we save that tent's latitude and longitude and size and angle in OpenStreetMap XML, ready for when we render it later. And as usual, all algorithms are on Wikipedia. I've got two more points to cover. I'm going to try and go very, very fast. So text labels. This is a cautionary tale, this one. So we need to position our text labels in an attractive way to label the things on the map. And positioning labels is pretty difficult. We do know which tent or tents a label is associated with. And we know that labels clashing with each other, overlapping, that's bad. I did build a visual editor for positioning the labels, so I could just go and do it all by hand. But I'm a developer, I yearned for automation. So I thought, I looked into it. The algorithm for positioning things like this is called simulated annealing. And so I wrote some. It's a lot of code. And I'm not going to go into much detail at all about this. But essentially, what we're trying to do is put text labels so they don't overlap and they're near their target. So simulated annealing has this energy function, which is the badness of a label's position. So more badness if it overlaps or if it's too far from the target. And then you run the simulated annealing, and essentially, for each step of it, you randomly move a label a bit. If it's better, if there's less badness, you accept it. And if it's worse, you sometimes accept it. You start by accepting things more often, and this is based on randomness. But then as you go further along and run more iterations, you start requiring more improvements. And the reason for sometimes accepting the worst ones is to avoid local minima. And simulated annealing, it takes ages to run. I mean, I didn't code the algorithm very optimally, but we're still looking at 10 minutes on this MacBook Air, and the results still needed tweaking. So this is a cautionary tale for why sometimes using what should be the optimal algorithm isn't necessarily the best thing. So I made a simpler algorithm, and this is just me. This isn't a Wikipedia one. So I've got two kinds of labels. One's for businesses and one's for groups. Businesses labels always go horizontally, whereas the group ones can rotate on my map. So we position the business labels first, and for each one, you try 8 positions to the left, to the top, to the right, and to the bottom of the business's icon, and single or multiple lines. And we pick the best position based on the least overlap with existing stuff. And again, we're just doing this in a random order. We're not going back and redoing anything. And for the group labels, we calculate the ideal position rotation, and then if there's a clash, we move it 5 meters away and try again. It's not recursive, there's one pass only. And the interesting thing is, the output does still need hand tweaking, but its result is actually better than simulated annealing, and it runs pretty instantly, so close enough. Last thing, this is just a quick teaser. So my scripting language, I would love to do a talk on it. That's another talk's content. But I know about scripting the drawing of maps from back when I worked on this app called Timeline World War II. This was released about simultaneously with the first Retina iPad, so 2012 or something. And writing a scripting language to style your map, to take the data and do things with it, it lets you easily iterate on design, and it sort of makes things really flexible to change. And so I use for my language, I use a package called Swift Parsing. Again, not going to go through this. Look into Swift Parsing. You can write a parser for stuff. I wrote a runtime that handles variable assignments. The script can call Swift code, passes images around as core images, can apply core image filters, which mean that I don't have to write things to do blurring or filling with textures. So I can easily play with new colors and designs by writing and changing the script, writing a new script. Everything's modular, and it outputs image files. So that's why I did that, and it has really helped pull all the aspects of this app together. Any questions? Okay. Sure. Oh, shit, sorry.
We did get some questions, and Amy will answer those online. One of the biggest questions is this close enough. The Earth close up is fairly flat. How small is your region so that you can ignore all the projections and calculations like that?
Well, the region for the actual LARP camp is a couple of kilometers wide.
But I mean, in general, for them, if they're doing this, at what point can they say, well, that's close enough?
It depends how much you mind. Once you're into the sort of multiple miles, tens of miles, and that kind of thing. Projections might make a difference, but it might not make a big enough difference to care. Once you're into the size of a country, it probably will.
I need to say that the actual question asked was, isn't the Earth flat already? Please thank Amy.
Thank you.